Go. Welcome AP chemistry students. Once again, we are going over chemical kinetics. This is part 2, and we're looking at the effect of concentration on the reaction rate. Some of the things that we addressed earlier on is there are some things that affect reaction rate, and they were going to be the surface area of the compounds that are used. The temperature was another, and then also concentration. And in this section, we're going to focus on the effect of concentration on the reaction rate, and in particular, look at the rate laws. Okay, so as we look through this, we see that the rate of a reaction often depends on the concentration of one or more of the reactants. When we look at the concentration, we have to see how the change in concentration of a reactant or the reactants, and they may not react, the change may not affect the rate the same, affects the rate, all right? And so we have this sample reaction, A to products, all right? And this is only a single reactant. And so as long as the rate of the reverse reaction is negligibly slow, we can express the relationship between the rate of the reaction and the concentration of the reactant, called the rate law, as follows. And it's showing you rate equals Ka to the N. So I would not necessarily want you to write down everything that is listed here, but you definitely need to know that the rate for this reaction, A to products, would be expressed as rate equals Ka to the N. Then your question may be, what does K mean? What does N mean? And that's on the next slide. All right. And so we go to this, and we see that K is a proportionality or a constant of proportionality called the rate constant. So we just call it the rate constant. That's what I would say. K equals the rate constant. And then N is equal to the order of the reaction. All right. N is equal to the order of the reaction. So when we look at these values of N, I have defined the meaning for them for 3 different orders: 0, first, and second order. I would not write all of this. I would just know that N equals 0 is a 0 order reaction. N equals 1 is a first order reaction, and N equals 2 is a second order reaction. Now, they do have the definition of 0 order with this, and 0 order does mean that the rate is independent of the concentration of A. And again, we're going back to that sample equation where A to products. And so if we change the concentration in a 0 order reaction, the rate will remain constant. If we change the concentration of a first order reaction, then the rate will change directly proportional to the change in the concentration. If we change a second order, then we are going to see the rate change proportional to the square of our change in the concentration. Okay, and we'll see what that means as we move forward. But N equals 0, 0 order, N equals 1 is first order, N equals 2 is second order. So what does this look like? So if you notice this, this part of the slide, we are talking about a 0 order reaction. And you will notice that this is a purple line, and we have a purple background. That's just genius. Whoever made this, genius. Okay, not needed to be said, but should be noted. Okay, so in a 0 order reaction, the rate of the reaction is independent of the concentration of the reactant. So what we're looking at here in this graph is concentration versus time. So even though the rate will not change, all right, even though the rate will not change in a 0 order reaction, the compound is consumed. And so the concentration decreases over time, all right? And that's what this is showing. This is going to decrease over time, and it's very linear. It's even though the concentration is decreasing, it's decreasing at the same rate the entire time. Now, that's hard to see here, but your change in concentration over time gives you the same rate regardless of where you're at. So this is a very linear plot. When you go to a first order, what happens is you see there's a change in the concentration. And so as the change in concentration happens, you see that the change becomes slower and slower. You see this small curve here. And then also with a second order, the change becomes slower and slower because these two are affected by rate, where zero order is not. Okay, now another thing that is important, and this is stated on the slide, is that, and you should know this, and I have a couple students in here, but anytime you have something to the zero power, you should know that that equals what? 1, right? And so because that is always a true statement, when you have a zero order reaction, the rate is going to be equal to the rate constant, because the rate constant times 1 is the rate constant. All right, and there's no going around that.